Hello everyone, good morning. Welcome back. Today we're going to be doing lecture 6. It's the continuation from previous lecture, alkanes, cycloalkanes, and then we're also going to do a little bit of stereoisomerism today. So let's go ahead and get started. Let's see here. Switch to presentation mode. There we go. Lecture 6. And next. So before we get too deep into lecture 6 here, I wanted to revisit a slide that I incorrectly explained in the previous lecture. And for those of you who have already seen the previous lecture, lecture 5, I apologize for that. I was explaining this like it was actually a chart that was based on heat of fusion and not heat of combustion. I got a little confused because I'm a little hard at math because I'm Asian and all, and I didn't even realize that those numbers there were like negative signs. And so, in fact, if you recall from general chemistry, heat of fusion is the amount of energy required to input into a molecule for it to do something, for it to break, for it to evaporate, for it to do whatever, right? Whatever a molecule can do. So that's what heat of fusion is, and that's what I was explaining in that slide. This chart that I was explaining that for was definitely not a heat of fusion chart. This chart is actually a heat of combustion chart, which I freely admit I totally confused there. And in a heat of fusion chart, what you're doing here is you're demonstrating, you're displaying, or illustrating rather, how much energy is released from a molecule, right? And so in a chemical reaction, or in this case, a combustion reaction. And that's why the numbers here are actually negative charges. If you remember from Gen Chem, when you intake energy, right, or when a molecule absorbs energy, then what happens is that the number, right, the delta H is actually positive. And then when it releases energy, it is actually negative, right? So that's the difference between, for example, an endothermic reaction where heat is absorbed and an exothermic reaction where heat is expelled or released. And in this case, we're talking about heat being released because they're all negative numbers. So I apologize for that. But if you haven't already seen Lecture 5, then don't worry about it. I've already gone through and deleted that part of the lecture so that you don't get confused when you're going back through the lectures to review everything for your exams and stuff. Also, there won't be, there haven't been, or there won't be any questions on any assignments or any quizzes about that particular part of the lecture, that slide right there, right? Expect something like, maybe there might be something about it on the test, on the exam, in 4 days. But as far as quizzes or assignments, don't worry about questions about that. Okay? So, let's go ahead and explain this chart then. So what's going on here is that it's showing you that the more stable molecules are actually the ones that are more branched, right? The ones that are releasing the most energy when they combust are the ones that are more flat and not unbranched, right? So in this case, I forgot what these are already. 1, 2, 3, 4, 6, 7, 8. So that's octane right there. 8 carbon, so that's octane, right? And octane, when it combusts, right there, that's a combustion reaction because it's being combined with oxygen, right? It releases that much energy, right? Negative 5,470 kilojoules per mole, which is a lot of energy, and that's why a form of octane, specifically isooctane, is used as gasoline. Okay, and I already forgot what molecule this was. 1, 2, 3, 4, 5, 6. It's a hexane. There's a methyl there. There's a methyl there. So that's 2,5-methyl dimethylhexane, and it's slightly more branched than octane is, right? Still the same number of carbons, but slightly more branched because it's shorter, and so it releases about 10 kilojoules less than octane does. Okay, and then for this molecule here, 1, 2, 3, 4, which is a butane with methyl groups on the second carbon and the third carbon, so 2,2-dimethyl 2,2,3,3 dimethyl 2,2,3,3 dimethyl butane right here, right, is only when it combusts with oxygen, it only releases 52 kilojoules per mole, which is 8 kilojoules per mole less, right, than this molecule. Okay, and what it's showing you here is a natural, not natural, but a normal routine combustion reaction where if you have a hydrocarbon and you combust it with oxygen, right, your products are CO2 and carbon dioxide, CO2 and water, because carbon dioxide is CO2. Okay, so that's what this thing is. This chart is explaining, and I apologize for confusing that in myself in the previous lecture and confusing you as well. But again, if you haven't seen lecture 5 yet, you don't even have to worry about it because I've already removed that part out of the lecture video, and then there won't be any questions about it on the upcoming assignments or quizzes. Right? Make sure you know it for the exam though. Okay, so let's go ahead and get started with today's lecture. I've got my trusty textbook here because we're going to be going through some numbers and some charts and stuff like that, and they're not all on the slides, but I'll write them so you know what the numbers are. But I definitely don't have these things memorized, so that's why I have my book open. That's why you should have your book available too, while we're going through these PowerPoints. And you know, what's my saying? What's the point of memorizing anything when you can just look it up in the textbook, right? And charts with numbers on them and data, experimental data. That's one of those things that you definitely don't have to memorize. Okay, so looking at cycloalkanes now, their angles, their bond angles, and the torsion strain related to those bond angles. We have here a cyclopropane, cyclobutane, cyclopentane, cyclohexane, cycloheptane, and cyclooctane. So all these alkanes, right? All these cycloalkanes, right? They're at their very heart alkanes, which means they're carbons that don't have any double bonds in it or triple bonds. And so if it's only got a single bond to it, right, there are 4 electron domains, steric number of 4, which means they're going to be sp3 hybridized, right? And when a carbon is sp3 hybridized, its shape is tetrahedral, and its bond angle is 109.5 degrees, right? So when you take a look at these cycloalkanes here, a lot of these are all very strained angles, aren't they? Right? Especially cyclopropane here, right? If cycloalkanes are flat, each carbon ring would experience a lot of angle strain, like it says, right? Even the cyclobutane, the cyclopentane, not so bad. It's pretty close to 109, right? But it even has to bend a little bit, and we'll see that in a second, that it has to bend a little bit just to maintain the 109 degrees, right? And then cyclohexane here, 120 degrees, pretty close to 109. Again, it bends to be more stable, but now we're going way beyond, right? The bond angles for a tetrahedral carbon. Right. Also, if the ring is flat, then the carbon-carbon bonds would be eclipsing rotamers, causing considerable torsion strain. Right, meaning they would be twisting. Right, they would be twisting. So this is a chart of the heat of combustions for all those cycloalkanes, which is the reason why I wanted to go through that previous slide with you from the last lecture again. Right. And you can see here what I told you in the previous slide about the heat of combustions, right? The corrected one. Cyclohexane here is actually the most stable of them all, right? It's got the lowest energy of them all. And that's because it can conform and change its shape so that it can more or less maintain that 109.5 degrees, which is the most stable for the most energy efficient for a tetrahedral carbon. And again, pentane, cyclopentane, pretty close to, it's pretty low as well, right? But definitely the ring size of 6 carbons is the most stable, right? The lower the heat of combustion, the more stable it is. So let's take a close look at cyclobutane. We actually have cyclobutane here, and we have cyclopropane here. but this slide will be mostly about cyclobutane. And I took the liberty of building a cyclobutane and a cyclopropane for you here, these molecules here. Now let's first, since this slide doesn't really talk much about cyclobutane, let's first look at this cyclopropane. Let's look at the cyclopropane, and notice, look at the bonds right there. They're bending, right, to form the trigonal structure of this cyclopropane, right? I mean, it's definitely flat, right, but it's bending pretty hard so that can maintain this triangular form. So you can tell then that these bond angles are very strained, and that's actually borne out in what? In the way that you see these overlapping orbitals are, right? These overlapping orbitals are, right, from carbon to carbon to carbon, right? They're actually bending the exact same way that they are on cyclopropane, right? And it's a triangular molecule here, right? So each one of these is going to be whatever 360 is divided by not 360. What is this bond here? I can't even remember what the bond is for an equilateral triangle. I mean the angle. What is the angle for an equilateral triangle? 60 degrees, I think. I think it's 60, right? Correct me if I'm wrong in the comments below, but that's math, right? So I think that this is a bond angle of 60, which is super smaller than. Oh wait, it says it in the previous line. I forgot. Yeah, 60 degrees. Yeah, so these bond angles right here are 60 degrees, right? Way smaller than the one on 9.5 that we need, okay, for cyclopropane. So then we have, now let's talk about cyclobutane. If you want to read more about cyclopropane, it's in your textbook, right before cyclobutane is cyclopropane in the textbook. But so here's cyclobutane right here, and I'll actually, well, I don't need to zoom out because there's nothing that you can't really see in the small screen right now, but there will be other ones later that you'll need to see. But notice here, right, it's definitely a square looking thing, right? And what you notice here is that in this particular structure, right, remember when you have wedges that are solid like this, it means that these bonds are coming out at you, right? They're not in the plane of the board, okay? So that's why it looks like that, and that's why it looks like that when I show it to you in the video right here. I'll actually switch views real quick just so you can see, right, just like that, right? That's how you see it in the picture too. So those dark wedges, right, that are in the front right there, they're these wedges, right? I'm sorry, it's like, is it not focusing? There we go, focused, right? This guy right here, this guy right here, this guy up here, and this guy right here that are coming right out at you. Those are the dark wedges here, okay, on the cyclobutane. Right, so cyclobutane is 27 kilojoules less stable than cyclohexane per CH2, right? And its bond angle right here, notice I said it was bending a little bit, right? It doesn't look like a perfect square, does it, right? It doesn't look like a perfect square. It's actually just bending a little bit, right? And that's why it's on a 90-degree angle right here in the bond inside. It's actually 88 degrees, which is still far below the needed stability of 109 degrees, excuse me, for a tetrahedral carbon. Okay, there is slight strain, torsion strain, like I said, because the adjacent CH bonds are never fully eclipsed nor fully staggered, right? And then the puckered formation has less torsional strain than a flat conformation, which is what I was talking about here. It's actually kind of bent right here. See, it's not completely flat. Okay, you can see that these two. Actually, let me go back to the half and half shot here. You can see that if I hold it straight, right, these two hydrogens are slightly higher than the two in the center, right? And so that's why it's a puckered formation. If it were flat meaning like this, it would be a lot less stable, right? So it's actually a little bit up a little bit, right? And if I leave it alone and don't mess with it at all, it definitely stays in its puckered formation. So this is one of the good things about having a molecular model kit. When you build these models right here, they're actually very accurate to the way the molecular geometry should be, even when you're adding bonds. You haven't seen it with the double bonds yet, but we'll see that later in the alkene section. Next, right? Next is cyclopentane. I have cyclopentane right here. Again, you see that it's not a flat molecule, is it? Right? It's not a flat molecule at all. And then the way you see it in there, in that picture, that drawn picture right there, right? The point of the house, or the pentane, the top point of it, is coming out at you right here with the solid, right? The solid wedges, the solid wedges, okay? Let me go ahead and switch to the half and half shot again. There we go, right? See how like if I turn it to its side, you see that it's kind of, I'm trying to make it so that you can see that it's bent up a little bit here. Wait a second, here we go. It's hard because it's a mirror image. Oh, that's actually a joke because we're going to be talking about mirror images a lot. I'm trying to make it focused. Come on, camera, you can do it. Focus. Focus. Ah, there we go. Okay. So notice how it actually, the tip of the top of the house, or the pentane, cyclopentane, points up a little bit, and the rest of it is flat, right? The rest of it is flat. Ah, there we go. That's what I was trying to show, right? So we'll rotate it this way so that the point of the tip is facing you now, right? And that's what it looks like on this picture that's drawn right here, okay? So cyclopentane, if I move my head, make my head a little smaller, figuratively and literally, no, I'm just kidding. Cyclopentane is only 5 kilojoules per mole less stable than cyclohexane per CH2 group, right? Which is, it's pretty close, right? Because remember, the bond angle for the bond angle for cyclopentane was it 108? Yes, 108 degrees. So that's why it's not that different. The difference in stability is not that different from the cyclohexane, right? Very little angle strain because it's nearly 109.5, right? And the slight torsion strain adopts the envelope conformation, and that's to avoid, and that avoids most of the strain, right? And that's that envelope conformation right here, where you have the tip of it kind of pointing up because it can fold down like an envelope, you know? So that's cyclopentane. I go through a lot to build these molecules for you, okay? So, and if you need to see them, you can always buy yourself a molecular model kit. They're pretty cheap on eBay and on Amazon. But if you don't want to invest in one of those, because, you know, other than teaching, this is the only time, I mean, I don't ever use these molecular model kits other than when I teach. So, yeah, the best thing to do maybe would be to do the, what is it called? QRChem.net thing, you know, the thing I showed you in the last lecture, and just type in these molecules' names and you'll see them in 3D space, just like you would see them in the, if you had the actual model kit with you, and you can play with it on your phone, right? Because we're all technological these days. Only, like I said, the only difference is you can't really change you can't have any rotation and stuff like that, but that's okay. All right, next. There we go. So the next one is cyclohexane, right, which is the most stable of all of those cycloalkanes. And I have so many molecules sitting up here, I gotta sort through them all. Here we go. Here's cycloalkane. Cycloalkane. It is a cycloalkane. Here's cyclohexane, right? And the thing to know is that cyclohexane, right, is actually, it is quite stable because it can adopt multiple conformations so that it can maximize its conformation with 109.5 degrees, the most stable and bond angle for a tetrahedral carbon. Okay, and so right now I have it not drawn, but I have it built, right, and it's at a what we call a chair conformation, right. So let me just go back to the full half shot right there, and you can see that it's like a chair, like a little recliner. Or I actually thought it was like a lawn chair. They call it just chair, but it's really like a lawn chair. Especially these days too, because I was actually spending most of the summer building a deck in my backyard, and man, that deck looks great. But I don't know if it actually conforms with like Arlington building code, but it looks awesome. But the point is, I got a lot of lawn chairs out there, and they look just like this, right? This is a lawn chair, and that's actually one of the structures that you see on this chart right here. So let me move back to the chart real quick. There we go. And you notice that at the very lowest potential energies, the lawn chair, right, is there. The lawn chair is the lowest potential energies of all the different conformations of cyclohexane. And that makes a lot of sense too, because not only are you maximizing your conformity to the 109.5 degrees bond angle of the tetrahedral carbon, you're also making it so you maximize the distance between all these different substituent groups, right? These hydrogens right here that like to hinder each other and block each other sterically, okay? Or repel each other sterically, right? So if you jump 145 kilojoules in potential energy, right, you can go to the half chair conformation, which is this. Again, this is like a lawn chair, right, where all I do here in the half chair conformation is I bend this up like this, and man, that was hard to do, by the way, okay, because it was already happy like this. Even this molecular model thing, right, it was already happy like this as the full chair conformation. But when let me just show you here, and I'll switch over to half and half, and make sure that it's focused. Okay, there we go, focused. And I'm going to try to bend this guy right here up. And when I bend this guy up here up, oh man, it's hard, right? It doesn't even want to go. Do you see how hard that is? And now it's half chair. Half chair is the highest potential energy, right? It's most unstable at 45 kilojoules per mole more than the chair conformation. It really doesn't like that, right? So the other thing that can happen is you can go back down a little bit here to where you're only 23 kilojoules per mole with the oops, let me move back to that. You're only 23 kilojoules per mole, right? Higher than the chair conformation, and that's called the twisted boat. And a twisted boat is when this chair even goes up a little higher than that, and it starts to twist like this, right? So now it doesn't look symmetrical anymore. It now looks twisted like this, okay? Right? And that's a little bit lower, right? But then it can continue to go to straighten out and become an actual boat like this, right? Like that. And you're jumping back up in energy again. Now you're 30 kilojoules per mole, 7 kilojoules per mole higher than the twisted boat, right? So before, you know, the legs of the lawn chair lifted up to make the twisted boat and the boat, right, and the flat, the half chair, but we're going through all the conformations. So now the twisted boat can go twist again, but it's going to twist on this side this time. So it looks like this now, right? So again, this is 23 kilojoules per mole, higher than the whatchamabie, the chair conformation, and then it can flatten out even more like that. So now I have my legs of my lawn chair lifted, right? I have my legs of my lawn chair lifted, but then my head is flat, right? Let me just show you that real quick. Right? And then what I can do now is then put my head all the way down like this, right? And I'm no longer at the highest energy, potential energy of the conformations, the half chair. I'm now at the full chair again at the very bottom of the chart right there, right? So those are all the conformations of cyclohexane. So, you know, you look at it from the top and it looks like a cyclohexane, right? You know, hexagon right there. But you turn it to the side and you see that it's actually a chair conformation, right? And that's the most stable version of cyclohexane. Good stuff, good stuff. Let's see here, back to normal again. So now we need to, it's a little bit more explanation here. Cyclohexane has no ring strain when it's in its chair conformation, right? The bond angles are approximately 109 degrees, right? 109.5 degrees. And there's also, there's also no torsional strain, right? Look down at both of these bonds simultaneously, right? And you can see that there's no They're the same. Okay? They're the same. It's kind of hard to show that on the thing there, but if you get one of these, you can do it too. The other possible conformations of cyclohexane have some amount of angle or torsion strain, right, or ring strain, but the chair doesn't. Okay, so now we got to practice drawing cyclohexanes in their conformations, right? Step one: draw a very wide V. And let me just tell you, when I was in undergrad, it was very difficult for me to draw the chair conformation of the cyclohexane. It was way easier to draw the boat than it was to draw the chair. Okay, I already feel like I messed up, so I'm going to try it again. Okay, there you go. And if you're printing out these notes, you should definitely practice on the notes. Okay, and draw along. Next thing, draw a line going down at a 60-degree angle, ending just before the center of the V. I'm going to guess that's 60 degrees. Okay. Then, draw a parallel line to the left side of the V, ending just before the left side of the V. So complicated. Okay. And then, draw a line parallel from step 2 down exactly as low as that line. Okay. Then connect the dots. The dots? What dots? Connect the lines, I guess. All right, let's try this. Let's see if I can do this. Okay. There's my wide V. There's my attempt at a 60-degree angle. There's my... Oh, I think I may have to go a little bit further because it's closer to the center. There we go. Then draw a parallel line, right? And draw this thing like this, and this like that. Hey, that's not bad, guys. I think that's pretty good, right? There's there's the bend in my chairs, right? The bend, the head, and the tail, or the feet of my chair. Try that again, right? I don't think that looked that great, honestly. Let's try that again. Yeah, I'm terrible at drawing chair conformations. Good luck to you guys, my students, on drawing chair conformations. Next, okay, so if drawn correctly, the chair should contain a set of 3 parallel lines, right? These lines here, of course. Oh, and they're using red, so you can't even see me draw it. These lines here, and then these lines here, right? They're all parallel lines. Each carbon ring has two substituents, right? When it's cyclohexane, then they're all hydrogens, but each carbon has 2 of them. One is the axial position, and one is the equatorial position. So let me bring back my cyclohexane. That's a lot easier to point out on than this drawing that I drew. That's terrible, right? So here's my cyclohexane, okay, and you see that there's these hydrogens right here. Okay, so the one that they're pointing at right now, right here, that hydrogen right there, is this hydrogen right here. Carbon. This carbon right here. Okay. Notice that there's a hydrogen popping up at the top right here, right? That is at the top. That's the axial hydrogen, right, or the axial substituent. So that's the axial one, and the one that's pointing to the side like this right here, that's the equatorial one right there. Okay, that's the equatorial. Okay, good stuff. Whew, okay, adding the axial substituents is easy as they point straight up and down and alternating around the ring. So, you start out by having the one go up right there, like this one right here, right? And then when you get to these carbons, right, right here, you have, or actually this carbon right here that it's pointing out right here is the one pointing out to you right here. This one right there in the front, right? And notice that it's going downwards just like this hydrogen is, right? And then this next one right here, all right, is this guy right here, and it's pointing upwards just like this one is pointing upwards. Okay, and then you can just repeat it all again on the other side. right? And then you have that, right? So notice that, again, just to review here, this carbon is right here, is this carbon right here, and that's the axial hydrogen, right? Then you move to the two carbons right next to that carbon. These are the axials down here, pointed downwards, just like these are pointed downwards. Then you get to the next two, the two axial hydrogens up here, pointed upwards, right? And then the very last one at the foot is pointed downwards right here, right? And so that's downwards there. So notice that your drawing of the chair conformation and its axials are, its axial substituents are consistent with an actual 3D model, right? Very consistent with an actual 3D model. Okay, so equatorial groups are drawn off the ring and they run parallel to the lines that in the chair. Okay, so let me actually make myself. Oh, I don't want to make myself smaller because you need to see that. Maybe I should do the half and half screen, and then yeah, that's good enough for now. Okay, so let's see how this is working here, how they have this drawn. So again, here we have our chair, and this red line right here, right, is this guy right here, okay? And then this red line right here, right, is this guy right over here, okay? This guy over here. So when you're looking at these equatorial hydrogens right here, you're talking about this one right here, right, is parallel to this one over here, right, back here. Okay, so when you draw that line, notice that bond right there is like this, right? Yeah, going that line right there. And this hydrogen right behind it is also pointed in that same direction. So that's this guy right here. And I know it's hard to tell, especially in a video, because you gotta get one of these and or look at it on the QRChem.net thing, right? So same is true of this one over here. That's talking about this. Where am I at? This hydrogen right here, or this bond right here, right? And notice that this is its trajectory right here. It's going like that. And what other hydrogen is also going that direction too? It's this guy right here. See, also going down that way too, right? So all you really need to know then, that if you're going to be drawing equatorial hydrogens on the chair conformation, just make them go pointed up and down, or down and up like this, right? Parallel to the bonds on the either side of them, okay? Not the bonds directly connected to them, but their neighboring bonds. Same thing is then true of these right here, these two bonds right here, right? So again, if we're looking at it like this, okay, and the equatorial hydrogen that we're looking at is this guy right here. Notice that this guy's like trajectory, right, is parallel to these bonds right here, and the same thing is also true of the trajectory of this hydrogen right here, parallel to those, right? So this hydrogen right here is this one. This hydrogen right here is this one. Okay? Good stuff. Last but not least, we have the hydrogens from the bonds from here and here, right? And you can see then that that would be this back here and this up here, right? So the one that is parallel to this one is that hydrogen right there, right? And then this hydrogen back here, right? I just got confused. I can't see what I'm doing here. Hold on one second. Gotta make myself small because I can't see what I'm drawing. Okay, let's try that again. So these bonds right here that they're telling you to be parallel with, okay, that's this bond right here. No, sorry, this bond right here. Okay, that bond right here, the one behind. Okay, and so the hydrogen that you're pointing at for this one is this one right here, the one that's pointing out in front. So this hydrogen is this one. Yeah, I was right the first time. Okay. And then for this one, it would be this bond right here. Okay, for this one, it would be this bond right here, and it's parallel to the hydrogen that's back here. See? Right there. That one right there. Okay. Again, I'm telling you, it's much easier to see if you hold this in your hands. Okay. So let me just do full presentation mode here so you can see the finished drawing. Okay. The axial hydrogens are all the ones in red, like so. And then the equatorial hydrogens are the ones I want to point out in arrows. And the important thing here is to draw those lines so that they're parallel to their neighboring carbon-carbon bonds, right? So this guy, for example, right here is parallel to this guy, right? This guy is parallel to this guy. This guy is parallel to this guy. This guy is parallel to this guy. These two guys here are parallel to these guys here, right? So make sure that you are drawing them parallel to a bond, a corresponding neighboring bond. All right, next. Okay, so monosubstitute cycle alkanes. What they are? What is a monosubstituted what is a monosubstituted cycle alkane? It is an alkane. Oh, let me bring myself back. There we go. It is an alkane, a cycloalkane, right, that has one of these hydrogens actually replaced with something else. And just for the purposes of that, I'm going to borrow a chlorine from my 2-chlorobutane here and make this molecule that it has showing on your slide real quick. Remember, X usually is some kind of halide, right, or halogen, so we'll use chlorine in this case. And so that's what that is right there, okay? I guess, no, I guess it's a mirror image because I'm in a camera. So this would be, why am I getting confused here? This looks right to me, right here, right? But then it's got to look right to you. So, yeah, now it looks right to you. Okay. It's what happens when I see it from behind and you see it from the front, right? Whew, okay. So this is the structure right here, right, that you see here. And what it's telling you here is that there are two possible chair conformations, right, where when you have a monosubstituted cycloalkane, where you can flip the chair, right, so that the head is now at the bottom and the foot is at the top, like this, right? And then, what happened here? Oh, okay. Like this. Oh, wait. Oh, I see what's happening. You can flip it, right, where the conformation changes, like so, right, with the bond rotation, like that, right, like that. There we go. And now the chlorine is equatorial, right? Whereas before it was not equatorial, it was axial, right? Let's do that again. My bad. I got a little confused there because I was seeing it on this side, but it's not your side. I got to remember that I'm in a camera right now, okay? So let's start it again. I'm going to start out with what it is when it was before the ring flip, okay? So here it is in my chair conformation, like this, right? And right now the chlorine, just like it is in the PowerPoint presentation, right? The chlorine is axial right there, right? And then I can do a ring flip, okay, through rotation of the single bonds, like that, right? And now the chlorine is in the equatorial position, right? No longer pointed upwards, okay? You can actually see these using the Newman projections as well. Used to be axial over here, then it becomes equatorial, or equatorial over here become axial through the ring flip, okay? And it's actually very difficult to see these in the Newman projection way because like you're looking down two of the bonds like this, see, like that, just like that. And that's how you see this little, right here, this little diamond right there, right? Which is the same as this little diamond right here. Right? Make sense? Good stuff. Okay, monosubstituted cyclohexane. So the point of this is that the point of this little ring conformation ring flip thing that we just did is that, right, when you have a methyl group there, right? And I wonder if I have a methyl group already made somewhere. Yes, I do. I'll just steal it from my propane. We're not using propane. There we go. When you have a methyl group there, right? This chair conformation with the methyl group in the equatorial position, right? This is methyl cyclohexane, right? Is the most stable. In fact, only 5%, right, of the time is it like this. Through bond rotation flipping, right? Only 5% of the time is it like this, right? But 95% of the time, it's like this. Oh no, lost the hydrogen. That's not good. That's not good. Almost lost that forever. There we go. Right? And it kind of makes sense too because when you have it flipped up like this in the axial position, there's a lot more steric hindrance. There's a lot of hydrogens around there, a lot of electron density around there that, you know, repel each other. So it's actually more stable like this. Okay? The axial position of methyl group causes steric interaction that destabilizes the conformation. I just said that. Okay, so let's talk about the 1,3 diaxial interactions. So what we have here is our monosubstituted cyclohexane, right, with a methyl group at position 1, the top of the head of the chair right there, right? And so when it's talking about the 1,3 diaxial interactions, I said that was the carbon 1, but that's just a carbon, sorry. But it's at this position, right? It's talking about this one and this one right here, right? Where the hydrogens, right, are pointed upward in the axial position, diaxial position, right? And then the hydrogen is also in the axial position right here, okay? And I'm just getting confused at which one's which again because I got to turn it around to see which one's which. But anyway, the point is, right? These these axial hydrogens are in the Gauss position, right? They're in the where they're Gauss, the Gauss position, right? And so, but when you change this so that you do the ring flip like this, and now the methyl group is in the equatorial position instead of the axial position, right? Those hydrogens and the methyl group are no longer in Gauss interaction, right? And there's a lot less steric strain, right? There's a lot less steric strain, which explains why when you have an equatorial methyl, right, it's much more stable when it's in the when you have a methyl, it's much more stable on a cyclohexane when it's in the equatorial position than it is when it's in the axial position, like that, right? Because of this diaxial interaction between the two methyls and the methyl group. And that X can be a methyl group, it could be anything. So here's a quick summary about cyclohexanes, right? Larger groups will cause more steric crowding around the axial position, excuse me, as we saw. And so in this particular chart here, talking about the 1,3 diaxial interactions, right? if you had chlorine as a substituent, right, the energy there is 2 kilojoules per mole. And so most of the conformations for a monosubstituted chlorocyclohexane, right, 70% of it would be in the equatorial position conformation, and only 30% would be in the axial position. Okay. If it was a hydroxyl group or alcohol, 4.2 kilojoules per mole, 83% in equatorial, 17 in the axial position. Methyl group, the one we just did there, right? This one right here, the 1,3 diaxial interaction, the carbon 1 right here, like I was saying, and the 3 position here, right? Right? 95% of it is in the equatorial. There we go, ring flipped equatorial. And then 5% would be in the other position where the methyl is pointed upwards in the axial position, like so. Only 5% like this. Okay. We have an ethyl group. It's even more energy, 96% to 4% to 4. Then we have I guess that would be an isopropyl, right? An isopropyl group, 9.2 percent, 9.2 kilojoules per mole, and 97 to 3. Now this is the interesting one here. We have a tert butyl group right there, 22 kilojoules per mole, 22.8 kilojoules per mole, and the ratio there is 9,999 to 1. So then that's a lot of steric hindrance when you have a tert butyl group sitting up there, right? And it kind of makes sense too, right? Look here, I have a free floating methyl group right here. Imagine that there, right? And it's all interacting with the, oh, I just broke it. Interacting with those interacting with those 3 position hydrogens, right? 3 position hydrogens. Conceptual checkpoint, 4.27, practice. So let's move on to talking about some di-substituted cyclohexanes, right? With multiple substituents, solid or dash wedges are used to show the positioning of the groups on the ring, okay? So this is pretty obvious, because we did this already before. If the line is nice and straight and flat like that, that means it's flat in the paper. And so a solid wedge means that chlorine is coming out at you. It's pointing up when it's laying flat. And then if it's a dashed wedge, like that methyl, it's pointing into the back of the page. Or if it's laying flat, it's going downwards, okay? And I actually thought I had an example of that real quick. Let me just draw this. Let me make it for you quick. That's what's great about molecular models, right? Okay, so we want the chlorine coming out, which is right here. We have chlorine. Right? Got the chlorine there. And then on the next one, the methyl is going down like that. Okay, so in this picture right here, and I'm going to switch over to my half and half shot here, right? This is what it looks like. Oh, it broke. Damn it. There we go. Rotate. There we go. Okay. So in that picture right there, this one right here, this is what that molecule looks like, right? Chlorine coming out towards you, right? And the methyl is over here going back towards me, okay? And then the rest of the molecule is in the plane of the paper, okay? Now we lay it flat like this, okay? Notice, right? Just like it says in the picture, the chlorine is pointed upwards and the methyl is pointed downwards, okay? Good stuff, right? So here we go. We have the cyclohexanes drawn in their chair conformations, okay? And here now we see this one is the way this one's positioned right here. The way I'm holding it is this right here, right? Methyl pointed down right there, and chlorine pointed up there, right? And then I'll do a little chair flip. Chair flip, right? Now the chlorine, is it pointed the same way yours is? No, it's not. There we go. Let me turn it around. There we go. Now, with the chair flip, well, there we go, chair flip. Finish the chair flip, right? The chlorine is equatorial, and so is the methyl. Okay? Realize that the chlorine group is up in both possible chair conformations, and the methyl group is down in both possible chair conformations. And what that means is that this is, you see how the chlorine is slightly pointed up there, and the methyl group is actually slightly pointed down, right? Good stuff. You can really visualize these things with the molecular model kit. Okay, skill builder. In Wiley Plus 4.12, draw both conformations for the following molecule. So we have a 1,3 ethyl methyl cyclohexane, right? And I think that actually I'm going to try not to draw it ahead of time because it might be the next slide. It'll be where it is. Yes, it is. See, so I don't want to do what I always do, which is jump the gun. Okay. So let's just read the instructions, right? It says first draw the chair by labeling the substituted carbons on the given structure, and then translating it into the chair, right? So we have here the cyclohexane, and we number the carbons 1, 2, 3, right? So we know that the ethyl group is on the 1, and we know the methyl group is on the 3. Okay, we'll draw our chair now, and we have the methyl group here, and then we have the ethyl group there, and then 1 carbon, 2 carbon, 3 carbon, and then the methyl group there, right? And if it's hard for you to tell which is which, what's going on here, right? Remember, this ethyl group here is coming towards you, right? It's coming towards you, which means it's always going to be pointed up, okay? In the axial position, up, right? And then this methyl group over here, right? It's dashed, so it's back, right? Which means it's going to be pointed down. And that's what you have there, okay? So let me actually draw that, or not draw that, but build it for you real quick. We'll switch out the chlorine here, and we'll put on a hydrogen there. Oh, am I out of hydrogens? Surely not. There we go. Hydrogen there, right? And then we'll put we already know that one of them is they're going opposite directions of each other, so let me find an ethyl group. There's an ethyl group right there. Okay. And so I'll take it off of this one here. There we go. Okay. And this one's pointed backwards. So you just go like this. Okay. So here's the molecule right here in 3 dimensions, right? There's your ethyl group right there pointed towards you, right? And then there's your methyl group right there pointed towards me, towards the back. Okay? And so we label it 1, 2, 3, okay? And then we turn it into its chair, like this, right? Like that, okay? And now we have the methyl group down here, pointed downwards, right? And the ethyl group over here, it's pointed upwards. Sorry, I rotated it a little bit. It's pointed upwards. See? Good stuff. Wait, actually, no. Something happened here. I changed the chair Okay, that was the one of the other chair conformations. Let's go to the chair conformation that's actually in the picture shown, which is this one. Because there's multiple. There we go. That's what I meant to show you. Yep, right there. See? And now the ethyl is pointed upwards, and the methyl is pointed back towards me now. Right? Is that the right way it's shown on in the video? No, sorry. That's how it looks. Right? Yes, that's correct. It's really hard because, like, I see what's in the camera feed, right? And I see what's in front of me when I'm doing what's in front of me, right? And the camera feed's like a mirror image, so I'm like, I'm not sure if I'm actually making these things the right perspective so it matches the picture on the screen, right? So carbon 1, the ethyl group, is pointed up, and then carbon 2, and then on carbon 2, the methyl group, carbon 2, should be carbon 3, typo. The methyl group is pointed down, right? Pointed down. Okay. To draw the other possible chair structure, we have to make sure that the ethyl group is pointed up. That the ethyl group, the pointed up one, will be equatorial, and then the methyl group, pointed down, will be axial. Right? So, okay. So what the heck just happened here? There we go. Okay. Kind of twisted on me. Okay. So we'll do the chair flippy thing again, like that. Now that's axial, right? I mean, sorry, equatorial. Now the ethyl group is equatorial right here, right? And then we pop this guy up here, like so, right? There we go. And now the methyl group, right, is axial. See? So those are the two conformations of a disubstituted cyclohexane, right? And you can draw them as such, right? The first one where the ethyl group is pointed up, the methyl group is pointed down, right? And then we do the chair flip, right? And now the methyl group is actually axial, and the equatorial group is the ethyl group is equatorial. No, the ethyl group is equatorial. So the question then is, which chair is more stable? You know, why? Well, remember from the previous slides that the substituents are more stable when they're in the equatorial mode, right? So that's one reason why. Okay, that's one reason why. But then you can also look at a chart in your textbook on page, I think I changed it because I was talking to somebody earlier. Here we go. On page 172, and it shows you a chart of diaxial interactions, right? And so you have the ethyl group here, which has a diaxial interaction of 8, right? And then you have so that's the ethyl group here, right? There's no diaxial interaction when it's equatorial, right? And then you have the methyl group, and its diaxial interaction, right, is 7.6. So which one's more stable? It's the one with the largest number not there, which is the equatorial group being the ethyl group, right? Because that's 8. When it's in axial position, it's 0 here. There's no diaxial interactions here when it's in the equatorial position. The methyl group, on the other hand, though, does have diaxial interactions, right? Because it's axial now, but its diaxial interaction is lower than it would be 7.6, right? Lower than it would be if it were 8, if it was the ethyl that was in the axial position, okay? So the more stable one would be the one with the ethyl group in the equatorial position. Okay. Whew, man. This just keeps on going. So I've been 19 slides, but I feel like I've been doing like 30 or 40 slides because like I've been building molecules and like showing them in 3D and stuff. So when naming disubstituted cycloalkanes, we use the prefix cis when you have two groups on the same side of the ring, and then we use the prefix trans when they're on opposite sides of the ring, right? Which makes kind of sense, right? So here we have cis 1,2-dimethyl cyclohexane because this cyclohexane is laying flat with the 3 front bonds going towards you, and the methyl group is on both sides, on the same side. But then the trans 1,2-dimethyl cyclohexane, right, has the methyl groups on opposite sides, right? So that's trans. These are called stereoisomers, by the way, and we'll get more. We'll get into that a little bit more later on in this lecture. Since they are 6-member rings, they are best represented as chair conformations instead of what we have here, just so you know. So continuing from the previous slide, when you have a cyclohexane with 2 substituents on it, right, and they're on the same side, like you see right here, it's really hard to do. There we go, right? On the same side, like this, right? And it's coming right at you, right? Like that. In the Hayworth projection, right here. Okay? Those are called cis, of course, right? But they can also be, not also be, but the other version is the trans version, which is like this, over here. Right? And what we're trying to learn from this slide here is the fact that when you do, right now, when you see these two right here, both of these methyl groups are in the axial position, right, on the trans, right? But when it does its chair change conformation, chair flip, like so. Hold on one second here. There we go. And then, there we go. Right? When you flip the chair, right, like that, where they're no longer sticking up and down in the axis positions, both are actually down now down in the equatorial positions. Makes it much more stable because both methyl groups are in the equatorial positions rather than they're being in the axial positions, right? But if you were to change this back to the cis version, like that, right? In this chair conformation, they're both still axial, right? And then when you do the chair flip, like that, they're both still axial. So the one with trans is obviously more stable, right? The 2 methyl groups being in the trans position on the cyclohexane is definitely more stable because it can have both methyl groups in the equatorial position. Whereas the one where it's cis, not as stable because no matter what chair conformation you put it in, you know, when you do the chair flip, they'll both always be in the axial. One will always be axial, right? And one will always be equatorial, right? So it's best to have everything in the equatorial position, okay? So polycyclic systems, there's declin, right? Declin is a 2-membered ring fused together, right? So there's cis-declin, 2 6-membered rings fused together. So there's cis-declin and trans-declin, right? Where the 6-membered ring is like this, right? That's cis. But when it looks like it's flat out like this, it's trans. And the reason why this is important is because declin is the substructure and found in many naturally occurring compounds such as steroids. So this is testosterone. The thing I want to point out here too is that all steroids are in a class of molecules in which they have this structure here where it's six-membered ring connected to a six-membered ring, connected to another six-membered ring, connected to a five-membered ring, right? So it's 6, 6, 6, 5. And that's a class of molecules called steroids. Okay? Fun stuff. Okay. So some other examples of some polycyclic systems, right? We've already seen the cycloheptanes in the previous slides, or maybe it was the previous lecture, I can't remember. But there's also camphor. I've heard of camphor before. Camphene, both of those guys are fragrant natural products, right? Isolated from evergreens. Polycyclic systems can also form these cool structures. This is a diamond network of six-membered rings all fused together. I can imagine that's a very, very strong molecule right there. Right? Looks pretty neat. It's a bunch of chair conformations, attached to each other. Okay. So we're still moving over into the next chapter now, which is stereoisomerism. Okay. So just a quick review. Isomers are different compounds that have the same molecular formula, right? Molecular formula. There are two general types of isomers. Okay. So there are constitution isomers, which we flogged like a dead horse in the previous lectures and tests and exams and quizzes and stuff. That's the one with the same molecular formula with different constitution, which is the order of connectivity of atoms. They're connected differently, right? And then there are stereoisomers, where they're the same molecular formula and constitution, except that they're different spatial arrangement, right, of the atom. And I'll show you what that means in just a second. So just so you know, the dimethylcyclohexane that we were talking about before, cis and trans, those are both, like if you were to look at its molecular formula, right? They have the same molecular formula. And then if you looked at its structure, like in 2 dimensions, okay, like in a line angle dimension, right, without the Haworth projection dark lines showing you that this is coming out towards you, right? Then they would look identical. So they would be isomers, right? But these are especially known as, they are stereoisomers though, because the CH3s are connected spatially different, right? They're connected spatially different. The cis, they're on both sides, they're on the same side, both are on the same side, and in the trans, they're on opposite sides. So that is a stereoisomer. And just again, we use cis and trans to denote between the two. Okay, to maintain orbital overlap with a pi bond, right? In the pi bond, a CC double bond, right? A carbon-carbon double bond, they can't freely rotate, which makes sense, right? Because if you had the sigma bond right there, then that was it. You can rotate freely, right? That's what we were doing with the Fisher projections. I almost said Newman projections. No, it's Newman projections. Yeah, that's what we were doing with the Newman projections. Rotating around that bond axis, right, and seeing them sterically hinder each other in the gauche and staggered and the eclipse mode, right? But for a pi bond, though, there's a second bond right there, right, between the two overlapping pi orbitals, and you can't twist this very well, right? This doesn't twist very well. And just to show you that, I'll break out my molecular modeling kit here and put a double bond together on 2 carbons and make ethene, or I guess I can make butene because that's the example we have. All right, and then, ouch, just hit something. Okay. Okay. So here we have butene, right? And if I turn like this, you can see that it has a double bond right there, right? And just imagine that one of these bonds is that hybridized sigma bond or hybridized sp2, right? Bond right there, making the sigma bond. But then this other one here is the overlap of the p orbital, making that double bond, making it a double bond, right? And notice that in this cis2 butene, right? These carbons, they won't rotate at all, right? They won't rotate. Let me maximize my head here for you to see. They don't rotate at all, right? Focus. There we go. Right? They don't rotate at all, right? Compare that to, for example, butane, not butene, but butane, which I'll make here. Oh, Jesus. I need a bond. 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 Okay. There we go. So here we have butene, right? The double bonded butene right here, and we have the single bonded butane, right? Notice that butane can rotate freely around the single bond in the center, right? The sigma bond, which is why we had those Newman projections where we were rotating it around like this, and we would have the eclipsed, we have the gauche, we have the staggered, the anti, all those different positions for the Newman projection, because you can rotate around the single bond. But on butene, since there's a double bond there, right? One bond is made by the sp2 hybridized orbitals that are making the sigma bond. The other bond is the overlap of the p orbitals. And it doesn't rotate at all, right? It doesn't rotate at all. So let me bring this back to the PowerPoint slide. There we go, right? And so, since it doesn't rotate at all, having this methyl group on one side like this, both of them on one side, you can actually move it around and have it on the other side. So now it's not cis anymore, it's trans, right? It's not trans anymore. It's not cis anymore, it's trans now, right? And these would be stereoisomers because they have the same formula, right? They have the same formula. They're connected the exact same way, right? But the methyl groups of the butene are opposite here in trans as opposed to being cis like this and on the same side, right? So butene, or anything with a double bond, can't rotate, right? Can have the ability of being a stereoisomer, okay? So let's identify the following pairs as either constitutional isomers, stereoisomers, or identical structures. And I made a note for myself. There's some answers on the next slide right there, right? So I'm not going to try to do it ahead of time like I always do. This is meant for you to be able to answer in class. So too bad we can't do that. It's a real disadvantage. Anyway, so let's keep moving here, right? So obviously when you have a cyclohexane with a hydroxyl or an OH on it, you can rotate that thing around, right? Like the ring, like this, right? And the OH will always be at one of the carbons. So those are identical. These two are identical, right? One just is pointed up and one is pointed down. Okay? You can flip it and it will still be the same on both sides. Now these are stereoisomers right here, right? Because one has them trans and the other one has them cis, right? So this one's a cis one and this is a trans one. Okay? These are constitutional isomers, right? Because they are the same formula, but they are lost my train of thought. Same formula, but not connected the same way, right? And then these two over here are stereoisomers. My head is blocking it. Let me change that so you can see. There it goes. These are stereoisomers here because on this one, this carbon here, right? Oops, not that carbon. This carbon there. This one's pointed down, so you could have it go this way, right? Or you could have it go this way, right? So these are two different spatial orientations. Okay, two different spatial orientations there. So those are definitely stereoisomers there. Okay, so here's some quick definitions when it comes to stereoisomers. The thing I really want you to get out of this is chiral. And an object is chiral when it is asymmetric, right? Meaning that it is not superimposable on its mirror image. So an example of that would be like your hand, right? Your hands are mirror images of each other, but when you put them on top of each other, they're non-superimposable, right? So that means they're not identical. They are identical, however, if they are superimposable, okay? So chirality is super important, right, because of like pharmaceuticals. And I have a really good example here because I've been having a lot of allergies lately. And so I've been taking a compound, I say compound, but I've been taking a molecule, I mean a drug, there we go, let's talk normally, a drug called Zizal, right? And I forget how you spell it, I think it's Zizal. Zizal is actually a stereoisomer of Zyrtec, right? It's a stereoisomer of Zyrtec, and let me show you why. Zyrtec. Everybody knows what Zyrtec is, right? So, I don't know about you guys, but whenever I take Zyrtec, it makes me super sleepy. But when I take Zizal, it doesn't make me super sleepy. And the reason this is because they both have very, very similar pharmacological effects, right? But they're only different by one tiny little thing, excuse me, which is what makes them stereoisomers, okay? So Zyrtec, the long-known allergy medication, is actually a molecule called cetirizine, which is spelled Cetirizin, right? And its structure looks like this. Cl, benzene ring, okay? And then that with a nitrogen, 6-membered ring, okay? And then this, that, and that with the alcohol, okay? Oh, and then there's another benzene ring up here. Okay, that is cetirizine, right? Specifically though, cetirizine, right, has its nitrogen right here as a dash, and it has a hydrogen coming out here as a solid wedge, which means then this nitrogen in this entire structure back here, right, this entire structure right here, okay, is going towards the back of the page, and then the hydrogen is coming out at you, okay, and then this part of the molecule here is actually flat with the page, in line with the page, okay? So that's cetirizine, that's Zyrtec, that's what's giving you your allergy relief, right? But Zyrtec makes me sleepy, so I take Zizal. Zizal is the exact same molecule, right, as Zyrtec, except it's called, I'm going to draw it down here, levocetirizine. Okay? And we'll talk about more level rotary molecules later, right? But it's called levocetirizine. Same exact molecule, right, as cetirizine, except this. The chiral carbon here, the one that's not symmetrical here, that makes it what it is that carbon right there. That's the chiral carbon. The one that has the benzene on it, and then the chlorobenzene on it, and then the nitrogen ring on it, and a hydrogen. Okay? So I'll just draw out this part. Yeah, just for giggles, let's draw out the whole thing again. Right? So Cl, benzene ring, right? And then these two right here are in the plane of the paper, so we don't have to really worry about that just yet, the two benzene rings. Okay? and then nitrogen. I'm going to leave that part blank right there where the bond is between the nitrogen and that carbon, because I want to show you the difference. Cool, right? So what's the difference? So in levocetirizine or Zizal, I really think that's how you spell it, but I could be wrong. You know Zizal, it's the one the commercial with the owl in it, right? In levocetirizine or Zizal, the nitrogen ring in all of its constituency comes out at you, right? It's got the solid wedge instead of the dashed wedge that you see up here. Which means then that the hydrogen now has a dash wedge. So it's going through the back of the paper, not coming out at you like it does up here. Right? And it's that difference right there that makes these two isomers? Yes, isomers. But specifically stereoisomers. Okay? And it's that difference right there in this carbon where one has the nitrogen ring and the rest of it pointing towards you, and the other one has a nitrogen going backwards, right, going on the other way, that gives it the different pharmacological effects. Both are awesome at fighting allergies, acting as an antihistamine, right? But for me, and maybe for other people too, this isomer, right, is makes me sleepy. But this isomer does not make me sleepy. So I'll take Zizal over Zyrtec anytime because I don't need to be sleepy in the middle of the day because of allergies and I'm taking allergy meds, right? So that's why molecular chirality is so important. And there's even other examples of this too. I can't remember specifically what the name of the molecule was, but back in the day there was like a birth control molecule, I think, and one was causing like aborted babies, and the other one, I mean, it worked, right? The birth control worked, right? But like one worked as a birth control, but the other one actually had babies being born, but they were all like deformed. I can't remember the name of the drug now. Comment down below in the comment in the comments below if you're watching this on YouTube and tell me if I'm right about that and what molecule that was or what drug that was, what birth control that was, where one, this is, you know, before they were separating out these stereoisomers, and so they didn't know what was going on, and one stereoisomer was actually was actually effective at birth control, but the other one actually still allowed for babies to be babies to be conceived, and then but they were born with birth defects, and I can't remember which one is which. All right, and what the name of it was. So again, chirality definitely has a huge impact in pharmacological studies. So let's talk more about mirror images, okay? And I'm proud to show you that I built these for you here. See? Look at that. See? So I'm not sure what the color coordination is going on with this particular image because generally oxygens and hydroxyls, alcohols are red, so that's correct, but usually hydrogens are white, but for some reason they have the ethyl group as white this time, and then methyl groups and ethyl groups are just no colors at all. But they've done gone messed up the color here, but that doesn't matter. I think they only did the colors here so you could clearly see the difference. So, and let me go halfway first, like half and half image here, so you can see that. There we go. So the molecule that's not the image, not the mirror, this one right here, right, is this one right here. See, I have to even check to make sure I got it right here. There we go, there we go. Yeah. Yeah, it's this one right here. It's this one right here, okay? This is the molecule, okay? So to me, it looks like that, but you need it to turn this way for you to look like what you see up there. There it goes. That's what you see. Yep. Okay. And then its mirror image is this right here, right? See the hydrogens in the back, or the whatever that is, ethyl group in the back, right? Its mirror image is this. So the point is, right, when we're talking about mirror images, okay, they're stereoisomers when they're mirror images of each other, and when you take them out from being stereo images of each other and you put them together, right, like this, they're not superimposable. And the reason why they're not superimposable is because even though the hydrogen in the back, or the ethyl in the back, and the oxygen at the top are the same, notice that these two molecules here have the blue thing, which is the hydrogen in this case, and the green thing, which is the methyl in this case, on opposite sides, right? So that would be an example of a non-superimposable mirror image. We have the mirror image here. They look the same in the mirror, right? But when you put them on top of each other, they're definitely not the same, right? Green and blue on one side, green and blue on the other side. If they were superimposable, then both greens would be on one side, both blues would be on one side, right? Which is the picture that you see here, right? Make a handheld model to prove to yourself that they are not superimposable, which you can't do because you probably don't have this molecular model kit, but I showed you in the video. Okay, so some practice here. I'm getting some text messages too. Let me check and see what that is about real quick. Okay, so what was I saying? Oh, this is about chiral centers, right? So notice that all of these here are chiral carbons, right? Because they all have different substituents coming off of the chiral center, or the carbon in the center, okay? And so here, it's got a chlorine coming out at you, right? And since that chlorine's coming out at you, that means that there's a hydrogen going backwards, right there. And then on one side it has a methyl group, and on the other side it has an ethyl group. So that's chiral. Here, OH, hydroxyl or alcohol coming out at you, which means there's a hydrogen going back into the page, and then a ethyl there and a propyl there, right? And then same thing here. We have a bromine coming out at you, which means there's a hydrogen going back into the page, and then on this side we have basically a propane, right? But over here we have a propene, right? So the moral of this slide is that you know the carbon is chiral if it has 4 different things connected to it, okay? Steel Builder 5.1, locating chiral centers, just for you on Wiley Plus. So let's practice. Let's draw, the chiral image of this compound. What? Let's draw the mirror image of this chiral compound, right? So it would be like this. Like that. Did I do that right? I think so. Okay. Okay. So a new word to know is that when you draw the mirror image of a chiral compound, that's called an enantiomer, right? So when you have 2 stereoisomers, they're enantiomers of each other. Okay? Oh, crap, I did it again. I didn't know I didn't know they were going to draw it for you. Anyway, so yes, these are enantiomers of each other. The mirror image will be its enantiomer. That says enantiomer, right? This word right here. Right? Enantiomers are 2 molecules that are mirror images but are not superimposable. Therefore, they're not identical. Only a chiral compound can have an enantiomer. Cool stuff. So we have some examples of some enantiomers here. Here we have a 2-chlorobutane, and this is an enantiomer, of course, because chlorine here at the 2 position is in one dashed wedged up, and the other one is dashed back, right? So those are definitely enantiomers, especially also because we have chiral centers here, right? And these are all different substituents, right? There's a hydrogen right there too, right? Different substituents, so that definitely makes it an enantiomer, right? This is also an enantiomer. We have a wedge down here that's pointing towards you, and then we have a dash right there, hydrogen pointing towards the back of the paper. That's an enantiomer, right? And we also have these structures here that are different, right? So that's definitely an enantiomer as well. Okay, that's definitely an enantiomer as well. Now, the difference, though, is that when we look at this structure here, okay, we have the OH coming towards you in one, and then we have the OH dashed into the paper going backwards in the other structure, right? But the thing is, though, that the rest of the structure is symmetrical, right? Unlike here, this structure is not symmetrical. Okay? So if you were to flip this over, you'd then have the OH pointed towards you, right? So it's not as so it's not just as easy as just making one dashed and one wedge to make it an enantiomer, right? And in this case, since they're symmetrical, they're definitely not enantiomers. These guys are identical to each other, right? But if you have a chiral center or an unsymmetrical molecule, an easy way to have the enantiomer of that molecule is to invert the dash and the wedges of the chiral center, right? Good stuff. That ends today's lecture. So the alkanes and cycloalkanes assignment will be assigned today, will be posted today, along with quiz 4. Both of those will be due tomorrow by 7:59 a.m. or 8 o'clock basically. That's June 10th, 2021. Reminder, there's also your exam 2 on Friday, and there's no lab today, so because it's Wednesday, and I will have a video up soon for quiz 2. Not quiz 2, quiz 3, right? For quiz 3 solutions. Good luck. Have a good day.